After we know the reason behind the radioactivity of each unstable isotope, now we're going to study about the rate of the decays or the rate of the decomposition of the unstable isotope or the radioactive isotope. If you look at the graph here, we're starting from 100% of mass of that kind of radioactive isotopes. So they kind of decomposes over time, but the rate of the decomposition is not really stable. It's not really constant. As you can see, it is like a curve. It's not straight line, right? There is a kind of value that we normally use for determine the rate or the speed of decomposition of radioactive isotope, and that value is called half-life. So actually half-life can be used with any kind of chemical reactions actually, or any kind of things. The meaning of half-life is the time required for a quantity to reduce to half of its initial value or initial state. So for example, if we're starting from 100% or 100 grams of your unstable isotope, so after it reduced to be 50 grams, this time required is called the half-life. Okay? So if you're starting from 50 grams of that kind of isotope, and then it reduced to the half of its original state of 50 grams to be 25 grams, it still have the same time requirement, 1T, right? So in total, from 100 to 25 grams, it would be 2T. And again, from 25 grams, the time required to reduce it to be 12.5 grams is another 1T. So as you can see, the time required here, or the half-life here, is constant, no matter how much of the radioactive isotope at the very beginning. If you're starting from 100, it will reduce to the half 50 grams by half-life, 1T. If you're starting from 50 grams, it reduced to 25 grams by 1T as well. So from the meanings, we say that at half-life, the number of nucleus at that time is equal to the number of the nucleus in the original state, NO, divided by 2. Okay, this is the meaning of the half-life. So half-life of any stable isotope, any radioactive isotope are constant. Okay, and I give you some examples of radioactive isotopes with different lengths of the half-life. For example, AG110. The stable isotope of silver is 108. This is 110. So the instability of this is caused by too many neutrons in the nucleus. So NO of P is too high. So basically, this one have to use a kind of beta minus decays, right? And as you can see, the half-life of this one is very short. It's 24 seconds only. And then for francium-223, these isotopes have longer half-life to be 22 minutes. Or copper is in hour scales, right? Copper 64 in 13 hours. Iodine-131 is about 3 days. But some of the elements have even longer half-life, like I'm sorry, this is not copper. This is carbon actually, carbon-14, which is very famous because we use that for radioactive dating, radiometric dating. Carbon-14 half-life of this is about almost 6,000 years, and for uranium-238, this is even longer, for the half-life as 4.5 billion years. This too is famous to be used as a tools to find the life what we call this as radioactive dating or radiometric dating. For example, if we found a kind of fossils and we want to know how old is this piece of fossil. So what we can do is find the carbon-14 or uranium, thing like that, remained in this fossil and comparing with the initial value. So then we know the age of this kind of thing, of fossils, thing like that. So for carbon, it is just suitable for something in the range of around 1,000, 10,000 years, thing like that. But uranium is using for something even longer than that, like kind of rocks that we found in somewhere, right? And we want to know the age of that kind of rocks. So we'll talk about it later. If you already study the kinetics of chemical equations, of chemical reactions, this kind of curve may be familiar to you, because the characteristic decreasing of the quantity of something in this kind of curve is controlled actually by the rate law equation. So if we have a kind of starting material, reactant, and then decomposes to be product like this, the rate equation we can calculate from the delta, or the amount of compound, the change in the amount of compound over the change of time, right? So we can write it up in the form of differential equation like this. So N is the number of nucleus of the reactant. So the dN by dt is the decreasing of the rate of decreasing of the starting material. But anyway, because rate is the positive value, but dN by dt over here is reducing over time, right? So it's negative value. So we put minus over here to change it to be the positive value, which is equal to the rate. Because the rate can be calculated from the dN by dt of the starting material or dN by dt of the product. But if you calculate from the product, the value here will be positive, right? It's very basic for the kinetics thing. So rate is equal to minus dN by dt of the starting material. And from this kind of curve, if you already study the kinetics, you know that this one, or this character, belong to the first order reaction. But if you don't know, just remember that this is the first order reaction. The characteristic of decomposition of radioactive isotope is first order reaction. In first order reaction, half-life remain constant for every chemical reaction, and including the nuclear decomposition as well. But if you're starting from zeroth order reaction or second order reactions, things like that, the half-life is not constant like this. Our half-life of isotope, the radioactive isotope decomposition, is constant because it is the first order reaction. Why? We'll talk about it later. So come back here. We know that the rate is equal to minus delta N by delta T. And because this is first order, that means the rate is direct proportion to the number of nucleus of your radioactive isotope. So if it is the direct proportion with the power of 1, which is called first order, right? So if we want to change, to make an equation from direct proportion, we change it to be equal, right? But we have to put the k here in the equation. So starting from this one. Okay. This is related to this, okay? From the half-life value and from this equation, we can find the k, and then we can know exactly the amount of nucleus left behind after a specific time of radioactive decays or radioactive decomposition. So first of all, we have to change this form from differential rate law equation like this to be integrated rate law equation. So basically, you just move delta T up here and move the n down here and take integration for both sides. And at the end, you will find the relationships between between k and half-life. So it's your assignment now. First of all, I want you to find from the half-life of carbon-14, right? I want you to find the rate constant or K value of the carbon-14. So what you have to do is using your calculus knowledge to change the differential rate law equation to integrated rate law equation, moving n to the side, moving delta t to the side, and integrate, and everything will give you the relationship between k and t. You have to use this one as well. After you have that, now come to the radiometric dating. As I said, carbon-14 and uranium-238 or any other element with the half-life that is suitable to the fossil or the piece of objects that we want to know the age, we can do the radiometric dating by this kind of thing. So the question is, how old is a piece of wood? Okay, so think about a tree that was killed by a volcano, thing like that. So a piece of wood that we found, if we want to know the age of that kind of thing, we use radioactive dating. So first of all, think about the kind of living organisms, trees, or dinosaurs, or any kind of living organisms. Normally we breathe, right? We eat, and then we have kind of exchange of carbon from environment with ourselves. Okay, and carbon-14 is a kind of rare element. Okay, but the amount of carbon-14 is quite constant during maybe hundreds of thousand years, because carbon-14, even though it is a radioactive isotope and it has the half-life, it decays, it decomposes. But in our world, carbon-14 is regenerated every day by the cosmic ray. So the cosmic ray from the sun hits the nitrogen atom in the atmosphere, and that kind of reaction produces carbon-14. So carbon-14 remain constant by the production of this reaction in the atmosphere. So it gives up carbon-14, raising up, while equilibrate with the composition of carbon-14. So in range of maybe 100,000 years, carbon-14 is quite steady, right? But after the living organism died, like this one, the tree was killed by the volcano. So, or a dinosaur just died. So after the death of dinosaurs, it stopped eating, it stopped breathing. So the exchange of carbon or carbon-14 from inside the body and the environment has stopped. So carbon-14 in the body start to decomposes, but the trees that already died cannot take carbon-14 from the environment in, right? So the equilibrium is stopped. Carbon-14 reducing over time. So after we found this piece of wood, then we extract carbon-14 out of that piece of wood, and we found, extract carbon atoms, carbon elements from the wood. And from that carbon elements, we found that the ratio of carbon-14 is reduced. Normally carbon-14 and carbon-12, you have a ratio of that in nature, right? But now carbon-14 reduces to left just only 8% of the wood, the living wood nowadays. So from this information, we can find the age of this piece of wood, okay? But you have to find the rate constant first. If you know the rate constant, you can find the age of this kind of fossils, okay? So this is your assignment. Use your basic knowledge of calculation, calculus to answer the first question. After you have the first question answered already, use that information again to do the second assignment here. Okay, so have fun, and we'll talk about it later in the next video clip.